Hello, this is Dr. Kraus with an introduction to feedback control and specifically how to use it to make a small robot follow a line or a wall. Conceptually, this isn't really that complicated, right? If the robot is too far to the left, make it turn to the right. If it's too far to the right, make it turn to the left. And then maybe how far it turns or how hard it turns should depend on how far away it is from where we want it to be. But we do need to, as part of that, keep in mind that especially with the sonar, if my robot gets turned pretty substantially with respect to the wall, then my sonar might bounce off at a weird angle and give me weird measurements. So implementing those four things is, not a huge thing. So what students tend to do is I'm just going to try to convert those conceptual ideas into some if-then statements that make my robot do what I want to do. And it starts off going okay. And then we need to add more and more layers to our if statement to try to improve the quality of how it does what I want it to do. And I have all these special cases for when I need to just turn the control off and drive straight. And before I know it, I've spent a bunch of time on it and it's kind of working. And then my batteries die. And then I have to start over because nothing's working after I put in new batteries. And so this ends up seeming like a simple thing to start out doing, and then it gets painful. So I want to teach you about feedback control and specifically about how to do PD control. And I think initially some of that sounds intimidating, and so students don't try it, and that's why they go down this other road, and then it ends up just being way more painful. So yes, this is a little bit more complicated to think about, but it's going to make all of these adjustments for you automatically, and you're not going to need all of these if statements, and your life is ultimately going to go smoother if you do it this way. Most of us have driven a car that has cruise control. Maybe not everybody. I've certainly owned cars that don't have cruise control, and it's possible you grew up in a place where everyone takes the subway or something. But assuming you have, the idea is that the car, when you set the cruise control system, it doesn't just dial in a certain amount of throttle, a certain amount of gas to the engine and just kind of leave it alone. Because if it did that, when your car went downhill, you'd speed up. And when your car went uphill, you'd slow down. And if there was a tailwind, you'd speed up. And if there was a headwind, you'd slow down. So what it does instead is compares the speed that you've set to the actual speed. And then it automatically adjusts the throttle position based on that error signal. Similarly, in this class, you've experienced a servo and you've worked with servos and you know how they work. And so we'll use that to jump into more about feedback control in just a minute. So let's talk about some basics about feedback control. What is it? Why is it so powerful? And then eventually you need to know what are some things that can go wrong so you can avoid having some of the common problems on your project. So by the time we're done, I hope you know what feedback control is and you know how to apply it to line following or wall following of a robot. And I hope to also give you a brief foundational look at what feedback control is so that you can apply it in your later classes. So ultimately what we're talking about is we have some goal. We want the robot to be a certain distance from the wall. We want the line underneath the robot to be at a certain spot on the sensor, or you want the car to maintain a certain speed, or you want the servo to go to a certain position. And so you somehow communicate that goal to the system. It measures what's actually happening. So this could be your desired speed and actual speed. It could be your desired servo position and actual servo position. And then taking that measurement, and this is called the feedback loop, and so this is where we're feeding back, which is where the name comes from, the output, comparing it to the input and developing an error signal. This little symbol is what's called a summing junction, and so input 1 has a positive sign associated with it, input 2 has a negative sign associated with it, and then the error is the output. So input minus, or goal minus measurement is equal to our error signal. Somehow that goes into our controller. This could be a proportional controller for P control, PD control, proportional derivative control, PID control, or something even more complicated than that. Somehow this controller is figuring out how to take the error signal over time and convert it into an input. So if this is a servo, then this is a voltage going to the DC motor that gets measured by the potentiometer that actually causes the output of the rotation at the end of the servo or whatever. So controller is converting error into automatically adjusting the system input based on the error to get us our desired output. So again, specifically for a servo, we have some desired position. We use servo.write microseconds to tell the servo where we want it to go. And then it uses a potentiometer to measure where it actually is. And so it measures the error between desired and actual position, uses a PID controller to send a voltage to the motor turns the input to the gearbox, the output to the gearbox is the actual whatever thing at the end of the servo we're moving that's also connected to the potentiometer, and that process continues until the error resistor is driven to zero. So one of the things that happens a lot when students do this kind of ad hoc approach is trying to figuring out how to turn off the controller. With this approach, we don't worry about that at all, because if the error goes to zero, the voltage going to the motor will be zero all on its own. We don't have to do anything special to make that happen. So again, this line of code or something like it would set the desired position, and then internally, the PID controller is taking a potentiometer measurement, calculating an error, doing a PID, and all this is happening inside that tiny little blue box that you've been using. Now, talking in general about feedback controllers, could be a servo, could be cruise control, could be your line following controller, could be your wall following controller. Ultimately, in any of those situations, our goal is to drive an error system to zero by automatically adjusting the input to the system to give us what we want. And what we want is for the output to match the desired input. So like we said, there's an overly simple approach. All of this stuff I've been talking about sounds scary and intimidating, and so students don't want to do that. And so they start with something simpler, and it gets yucky and messy and painful. So yeah, this just isn't I understand it, but it's not a great approach. Let's not go down that road. So part of what I'm saying is let's start with proportional control. And what we mean by that is the controller is just going to be a gain, just some letter K that's going to multiply the error by K to turn it into the voltage that's going to the motor or whatever. And what that means is the farther away from the wall or the line I am, the more the robot is going to turn. So if I'm trying to do line following, and if I happen to have, this number could change depending on how many sensors you have and how many sensors you're using, but assuming that my desired position goes from 0 to 7,000, then the middle of that would be 3,500. So my desired position is to have the line centered directly underneath the line sensor, then I know I'm where I want to be. My actual position is going to come from using a line from the Pololu QTR sensors library to tell me where is the line. And so this could be any number between 0 and 7,000. So my error would then be desired position minus actual position. This could be a positive or negative number. And then I'm going to tell my robot how much to turn by taking a KP, which is the one number that I get to adjust, and multiplying it by the error and turning that into a turn signal. And if 1500 is the middle of my 1000 to 2000 range on my servo, then hopefully that means go straight, which means that turn signal could be plus or minus 500, where negative might mean turn left and positive might mean turn right, or vice versa. But this is all that I'm doing to actually send the turn signal to the servo. And like I said before, we don't have to come up with special magical cases on when to turn the controller off. That takes care of itself by the error going to 0. And so this adjustment on how much to turn is being automatically calculated for us based on the error signal. Now, one of the big challenges that you'll face to try to get this thing started, and if you don't get this right, nothing is going to go right, is trying to get the sign right, the SIGN sign. So, for example, imagine that you happen to have a desired position of 3,500, and you did the measurement, and you're actually at 2,500, which means my error would be positive. And KP should hopefully be a positive number, otherwise things are going to get weird. So my turn signal would then be a positive 100. We talked about it having a range of plus or minus 500 if we're using a servo. This is only going to work if having a positive turn signal causes the actual position to go up. If my line is here and I'm slightly off and my turn signal causes me to go the wrong way, then this number would get smaller, the error would get bigger, and I'd continue to increase my input in the wrong direction. So it's very, very important, and I'll go over an example of how to do this in a supplemental or secondary video of this. But we want to check out, how does the sign of the turn signal affect the output measurement? So if positive turn causes actual position to increase, things are going to go well for us. If negative turn causes actual position to decrease, then everything's right. If those are backwards, then we've got to correct that either in software or by switching some wires or something. But it must be the case that, because if our error is positive, it means we're too far away. And so we need this number to go up. If our error is negative, that means that our actual position was 4,000 or 4,500 or something bigger, and we need it to come down. And so if a positive input for turning causes the sensor measurement to go up, that is correct. A negative turning input should cause the measurement to go down, otherwise nothing is going to go well. And your robot will always be turning the wrong way, and it's either going to slam into the wall or slam into the outside wall. Another key issue, there's kind of two parts of this. How do I choose a decent KP, and then how do I make sure I don't have a saturation problem? And we'll define saturation on the next slide. So part of what we're getting at is that your KP is kind of a scaling factor between your sensor and your actuator. So if you're using a line sensor, the sensor values can go from 0 to 7,000, which, and if 3,500 is your set point, that means that your error can go plus or minus 3,500. But if we're talking about a servo that can go from 1,000 to 2,000 with 1,500 microseconds at the center, then your input can only go plus or minus 500. So your KP, maybe what you want to do is have it, so part of the issue is, when do you want it to have it to do a turn as hard as it can? Or how hard do you want it to turn with a certain amount of error? And so in this case, what if you wanted 0 to correspond to full left and 7,000 to correspond to full right? Then your KP value would need to be 500 divided by 3,500, or 1/7, so that my sensor value is always getting divided by 7 or multiplied by 1/7 to get to my appropriate command that I'm sending to the actuator. Now, it doesn't have to be that. Maybe you have some reason why you want it to be a little bigger, and that's what gets us into saturation. So if you were in this situation, you had 3,500 and you had an actual position for your set point, you have an actual position of 1,000, your error then would be 2,500. If my KP happened to be 1, and maybe I had a good reason for doing that, then I'm asking it to turn a value of 2,500. But if 1,500 is my set point, and I take 1,500 and subtract 2,500, I get a negative 1,000, or add 2,500, I would get a positive 4,000, which is not allowed. So that's where saturation comes in. If we said plus or minus 500 is the range that we're allowed on our servo movement for steering, then anytime we go above 500, we're going to check it and we're just going to set it back to 500. And anytime you go below negative 500, we're going to check that and just set it to negative 500. So if I have some maximum amount, and maybe you want this to be less for some reason, maybe your wheels run into your chassis if you turn too far, or the robot flips over. Maybe this is really only plus or minus 200 or something. But if my input is greater than my allowed maximum, just set my output to the maximum. That would be this range right here. If my input is less than negative maximum, then I'm just going to set it to negative maximum, which would be this range right here. Otherwise, I'm just going to leave it alone and let output equal input. So you'll need to write yourself a saturation function, and maybe if I'm feeling generous, I would show you mine, but this is really not that complicated to handle these kind of situations. Otherwise, you don't realize that you're asking the servo to turn way more than is physically possible, and that might lead to really weird behavior. It probably won't damage your servo. Who knows? But when you start sending a negative number, for example, does that cause because of 2's complement, the number to overflow, and all kinds of weird things can happen. So saturation is protecting you from asking for more than the servo can actually give you. Now, that's kind of in general how we would do it for line following. There's actually very, very little difference, practically speaking, especially code-wise, in terms of doing wall following. The only difference is now my desired distance might be a much smaller number if I'm using units of centimeters. Now, if I was doing microseconds from the wall and back, maybe the numbers are actually pretty similar. And then I would have some kind of function that's going to read my sonar and convert it to centimeters. Maybe that's only 2 lines of code. Maybe it doesn't warrant a custom function in your mind, but I want to push you towards custom functions because that's just kind of my thing. So write yourself a little function that reads the sonar and converts it to centimeters. Then your error signal, just like before, is desired minus actual. And so this would be a difference from the line follower. It's a different line of code that reads the sensor. Your set point would be a different number, but conceptually it's still just a number. And then your KP might need to be quite a bit different. So now my range maybe only goes from 0 to 20 instead of from 0 to 7,000. And so maybe my KP needs to be a lot bigger. But other than changing this set point and changing this function and changing the value of KP, nothing else changes as I'm switching from line following to wall following. It's still pretty much the same code. Now, P control can do a lot of really powerful things for you, and I would definitely encourage you to start there. Eventually, though, you'll have to make weird trade-offs of either I'm not getting that much correction and it's kind of going a little slow, or it starts to overcorrect and do some crazy things. And so there's adding a derivative term to the controller can really help you in those situations. So you may have heard the term PID control, which stands for proportional integral derivative control. But one thing that might not be obvious, we're talking about, so this is my controller, my PID controller. The output of that is the voltage that's going to my motor or the turning signal that's going to my servo or whatever. So that output is proportional to the error for the P control term. It's proportional to the integral of the error for the I term, and it's proportional to the derivative of the error for the D term. We're probably not going to do an integral term in this course. That's probably too complicated, and you don't need to be, because there's not any reason to be super accurate in your line following. Being pretty close is fine. So this is an unnecessary complication that we're going to not think about for now. So PD control is going to mean there's a term that's proportional to the error, and there's another term that's proportional to the derivative of the error. Now, depending on how much you love calculus and how much you thought about numeric differentiation, this might be a little weird. But remember, when we talk about the derivative, we're talking about the derivative of error with respect to time, sometimes called E dot, but dE dt in your calculus notation. And you may remember from calculus 1, I think, that your limit, so this derivative is the limit of change in error divided by change in time as, this should be a capital delta. I'm not going to take the time to redo that. But this doesn't make any sense. So it's the limit as capital delta T goes to 0 of delta E divided by delta T. So we're going to numerically approximate that in our C code by defining delta E as the error minus the error the previous time through our loop. And then we're going to define delta T as the current time, which we probably found using millis on our Arduinos, minus the last time when we went through the loop. And then our E dot is approximately delta E divided by delta T. So if I go to do that, so go back to line following. We've got a desired position of 3,500. We have an actual position. We define an error. Somewhere in the code, we're saving the previous error and the previous time, which were the last times we went through the loop. And so then we're finding delta T and delta E and error dot. And then when we go to send our voltage, calculate the voltage to our motor, our turn signal is Kp times our error plus Kd times error dt. Kind of screwing that up a little bit. But so adding in these lines to calculate the derivative of the error, or approximate numerically the derivative of the error, and then adding in this extra term is all that it takes. So I'm going to recommend that you start with P control and kind of dial your and start with a fairly small KP and increase it over time until you get that working pretty decently. And then add in KD if you feel like you're starting to see overcorrection and oscillations, but you don't want to have your KP go smaller. So this might be what it would look like to save the previous error and the previous time before you go into your calculations. Then you'd grab the current time, you'd make the current error calculation, and you would find your error dot, like so. And then your turn would be KP times your error plus KD times error dot. And then you would have a saturation function, which you would have to write, that would protect you from trying to oversteer. And really, that's all that it would take. So be aware of saturation is going to mess with you, and try very hard not to make your code have too many pauses in between the times that you're doing these control actions, because that's going to get really weird. So for example, I don't think we have this problem as much with RoboRace as we might with RoboSaki, but Sonar kind of takes a few milliseconds because you're reading that and sound has to travel a certain distance and that sort of thing. So just be aware of anything in your code that would cause it to have pauses between its control actions, because that can be really, really weird. So as I said, I'm going to make a second video in just a minute talking about how to actually do line following control, and I'll walk you through trying to verify your signs, and then we'll go from there.